Okay, we hear the ring, we hear the bell. That's the beginning of our lecture. So, first of all, thank you everybody who sent me your home assignment, your homework for week number 1. Out of 25 students, including those who are on distance study, 21 sent me their homeworks. Only 4 students failed to send their solutions in time. So the process goes on, and it's okay. There are just few mistakes I would like to mention. The mistakes which you make, not everyone, but some of you make when you send me the photos of your solutions. The first mistake, yes, please.
I sent mine in parts because the size. Okay.
Yeah, the first mistake is the size of the files. Avoid sending heavy files. Some of you sent me files, the whole homework, week number 1, up to 100 megabytes. That's nonsense. You don't need such a size of all your files. One picture, one image, or one photo may take about 100 kilobytes. One photo. And if you have about 10 photos, about 10 photos. So the whole work may occupy about 1 megabyte disk space. That should be a correct number, well, plus minus 20 to 30%, but not 100 megabyte. Please never send me such heavy files. We don't need it. We don't need so many megabytes and so many disks, so much of disk space. And there are a number of ways to reduce the size of your pictures. You can look into internet and search the internet for an appropriate way to reduce this, the size. It depends on the kind of smartphone you are using when making the pictures and the kind of applications which you use to edit the pictures. So there are multitude of ways to reduce the size. Please reduce the size of each picture down to 100 kilobytes, no more. Also, there is another mistake which some of you made. Some of you made something like this. You sent me a picture, a photo, and the sheet of paper occupies just a small part of it. And your formulas here on the sheet of paper occupy just this part. Well, the useful information is here, but all this is unnecessary. Please cut the margins of your picture and make the picture of only your homework, only your solution, your formulas and explanations. Don't include the margins and don't include the surface of your table. That's increasing the size of your file. That's an unnecessary information which leads to such huge files sometimes. So some technical details and some technical knowledge is required to send appropriate files of your homework. Please take it into account next time. So we were discussing the Newton's laws of classical mechanics. And the main thing you know is that the net force acting on a body equals the product of its mass and acceleration. Before Newton, people thought that a force acting on a body is proportional to its velocity. Before Newton, people believed that was a correct law. And that seems to be natural, by the way. because if you want to push the cart quicker, you have to push harder. You have to apply a larger force to increase velocity. If you want your boat to go faster on the surface of the lake, you have to row harder. You have to apply larger force in order to increase velocity. So at first sight, the force applied to a body seems to be proportional to its velocity. Our everyday life experience seems to prove it. But Newton was the first to understand that the force is proportional to velocity. The force applied to a body is proportional to its velocity because there are forces of friction, forces of resistance, which depend on velocity. The larger the velocity, the greater is the resistance of the surrounding medium. So in this case, yes, the force applied to a body will be proportional to its velocity. But the most fundamental law says that the force applied to a body of mass m should be proportional to its acceleration if there are no forces of friction, or if forces of friction are taken into account in this net force. That is a discovery, because for centuries people believed in this law, but finally it appeared to be incorrect. Finally, it was proven that the force applied to a body is proportional to the acceleration rather than the velocity. And this law, discovered by Newton, why do we believe it's correct? Because it was validated and proven in thousands of experiments, and very precise measurements prove that this law is correct. So we are sure that this law is correct because of many experiments, and many experimental results validate this law. We may ask a natural question: can this law be somehow derived theoretically, or obtained theoretically from other assumptions? Well, experimental verification is very good. That's okay. So we know this is correct. But can we derive this law from other theoretical assumptions? The answer is yes. Yes, this law can be derived. It can be obtained within the frames of Einstein's theory of general relativity. And also another way to obtain this law is in quantum mechanics from the Schrödinger equation. Sometimes you may learn how it can be done, but now, on your level of knowledge, when you are first-year students, you must simply believe that this is correct without any derivation, because this law is proved and validated by many, many experiments. There is also another important question concerning the Newton's law. Is it absolutely correct? Or maybe it's an approximation? Maybe there is more correct formula, and this one works well, but just in some domain of applicability, limited situations, limited number of situations. The answer is yes, certainly. This is an approximation. This is not an absolutely correct law. This is not an absolutely precise dependence between force and acceleration. In relativistic velocities, when bodies move at very high speeds, then the dynamics is different. It's not classical, it's relativistic, and all the formulas are different. So this is just an approximation for slowly moving objects. Also, if we look at the third Newton's law, that the force of action is equal and oppositely directed to the force of counteraction. If two bodies interact, then the forces with which they exert on each other obey the Newton's third law. If we look at this law, is it absolutely correct? No. Again, this is an approximation. And it can be easily understood if you consider, for example, two charged particles. For example, two positive charges. And there is some force of interaction between them, some force of repulsion. The magnitude of this force depends on the distance between charges and the value of charge of each charge. But if we keep the charges at some certain distance, fixed distance, then these forces will be constant. And then imagine that we suddenly move this charge very quickly to some other point. So this charge will be shifted to another point in space, and the strength of the electric field here will be different. It may be larger, and the force acting on this charge will change immediately. But this force will change not immediately, because the information about the shifting, about the move of this charge will go in space at the velocity of light, and it takes some time for the information to reach another charged particle. So another particle will know about the displacement of the first particle, and another particle will experience somewhat different force later, a little bit later, not immediately. So during some time interval, this law will be incorrect. Forces will be different, acting on two different charged particles. So each law has limited domain of applicability. Each law in physics is not an absolute law. It has a limited area, a limited number of situations when this law can be applied. So with these concluding remarks regarding the Newton's laws, we move further to study other laws of physics. To go to other laws of physics, I will write down the same Newton's law, second Newton's law. And I will recall that the acceleration by definition is the rate of change of velocity. The rate of change of velocity. Multiplying this equation by delta t, one obtains f delta t equals m delta v. This quantity has special name. It's called impulse of the force. Impulse of the force. And this quantity is called momentum, a change of momentum. Let it put it in this way. Delta v is the change in velocity. So delta v is the final velocity minus the initial velocity. And so all this is mass times final velocity minus mass times initial velocity. So this quantity is called momentum. Momentum of the body of mass m. And so this is the change in momentum. This is the change in momentum. Change in momentum. So we can look at this equation and we can read it in the following way. An impulse of the force acting on some body equals the change of momentum of this body. An impulse of the force acting on a body is equal to the change in momentum. The change in momentum occurs during some time interval delta t. It requires some time for the momentum to change. Impulse of the force equals the change in momentum. We have derived this equation from the second Newton's law. And this equation is very important because it allows one to obtain a very important law of physics, a law of conservation of momentum. Here is no conservation of momentum. The momentum is changing. There is a change in momentum. But we may ask the question when the momentum is conserved, when the momentum of the body is constant. And to obtain a somewhat general answer to this question, in general, the answer applicable in general situation, we will consider not a single body, but two bodies, two interacting objects. So let it be one particle of mass m1 and another particle of mass m2. And these particles have some arbitrary velocities, v1 and, well, anything v2. I try to draw an arbitrary vectors. They should not be parallel, no. Arbitrary vectors. Let them be not parallel, yes. v2. And so if these two particles interact, that may be a repulsion or attraction, anything. Let it be some sort of attraction, interaction between these two particles. The force F1 is acting on particle M1, and the force F2 is acting on the particle M2. As the particles move, they interact. Certainly, when the particles are at very high distance, the interaction is zero. When the particles approach each other and the distance between them is smaller, then the interaction is observable. And when the particles move away from each other at an infinite distance, then the interaction is again zero. So this interaction is switched on for a short period of time when the particles are not far from each other. Let's consider the equation for the change of momentum of each particle. So the first particle has a momentum m1 times v1. And during short time interval delta t, the momentum of the first particle will change according to the force acting on it. And the same is true for the second particle. So the force acting on the second particle times small time interval delta t equals the change of momentum of the second particle. If we add these two equations, we obtain F1 vector plus F2 vector times delta t equals m1 delta v1 plus m2 delta v2. Now recall the third Newton's law. A force of action is equal in magnitude and oppositely directed to the force of counteraction. So these two forces must be equal and oppositely directed. If we take this into account, we will immediately obtain that this round bracket equals 0. And so all this expression is 0. Provided there are no other forces acting on these particles. Provided only the internal forces are present here, only the forces of interaction between the two particles, and no other forces from other objects around them. We assume that there are no other forces. We assume that there are only internal forces in the system of two particles. And then, under this assumption, we obtain that the change in momentum of two particles occurring during time interval delta t is 0. That is, if we choose a very small time interval. Then, let's imagine the time axis. We have chosen a small time interval, delta t1. And during this time interval, the change of momentum is 0. Then we consider the second time interval, and again we will obtain that the change in momentum is 0. And then all other time intervals, and within each time interval, the change in total momentum is 0. So after we sum up all the changes in momentum during the whole span of time, we will obtain that the change in momentum is 0. Always, if there are no other forces from external objects. If there are only internal forces of interaction between the two particles, then the change of momentum is 0 during an arbitrary span of time. What does it mean, the change of momentum is 0? It means that the final momentum equals the initial momentum. That's the law of conservation of momentum for a system of particles. Certainly, we may consider much more particles. We may consider 3 particles interacting, or 4, or 5, or 100 particles, 1,000 particles. If they interact only between each other, the result will be the same. The momentum, total momentum of the system of particles remains unchanged. The final momentum equals the initial momentum, if no other forces from external objects act on this system of particles. What is the final momentum? m1 and velocity of the first particle final plus m2 velocity of the second particle final. And what is the initial momentum? m1 velocity of the first particle initial velocity plus m2 and initial velocity of the second particle. So this equation can be expanded to show what does it mean, what does it actually mean. In detail, the initial momentum equals the final momentum of particles. This is the law of conservation of momentum of the system of particles. Why this law is very important and very useful? Because we can somehow predict something about the velocities without consideration of forces. There are no forces in this equation. All the forces have cancelled. All the forces have cancelled. They are not present here in this equation. This is very useful because sometimes we know very little about the forces of interaction. Sometimes we know nothing about what was the force of interaction between the two particles. And we know nothing about how did these forces change in time. We have no information about it. So how can we solve the problem of interacting particles, colliding particles? Without even thinking about forces, we know something very important, law of conservation of momentum, which allows one to solve many problems regarding the systems of particles. And it does not require any knowledge about forces. We don't need forces, which is very useful, because sometimes we know nothing or very little about forces of interaction. Especially interesting and useful situation occurs when two particles collide and stick together. Imagine two particles, m1, moving at velocity v1, and particle m2 moving at velocity v2. And we know that these particles somehow collide and stick together, forming a compound particle consisting of two particles together, stuck together. Yeah, what's the question?
It was two objects, we call it coupling.
What?
Coupling.
Coping?
Coupling.
Coupling, yes, coupling. The two objects stick together and remain coupled, yes. That's very often, that happens very often. So in this particular case, we don't know the forces of interaction when the particles stick together. The forces may behave very. The behavior may be a complicated function of time, but we don't need forces. We have the law of conservation of momentum, and this law allows one to calculate what happens later after the particles collide and form a compound particle with mass m1 plus m2, a compound particle. So after the interaction, this compound particle will move at some velocity v. And the law of conservation of momentum says that the initial momentum equals the final momentum of the system of particles. So the initial momentum was what? The initial momentum of the first particle plus the initial momentum of the second particle. And the final momentum was what? The total mass of the two particles stuck together times the velocity of this compound particle as a vector. So from this equation we can find the velocity of this compound particle. The velocity of compound particle will be easily found from here as m1 v1 plus m2 v2 in vector form divided by m1 plus m2. That's the velocity of the compound particle. If we know the masses and velocities of the initial state consisted of two separate particles, and the final state consists of one compound particle. Let's introduce a new notion of vector r defined by the formula m1 vector r1 m2 vector r2 divided by m1 plus m2. So what I mean is that we have two particles m1 and m2, and we have some system, some frame of reference with origin in point O. And so in this frame of reference, the first particle has its own radius vector, and the second particle also has its own radius vector, r2. So r1 and r2 are the vectors which give you coordinates of each particle. These vectors give you coordinates of each particle. You know, if you have a reference frame with axes x and y, and the origin and point O, then any vector u gives you coordinates x and y. And so if you have a vector, then you know, and some axis, then you know the coordinates of each particle. A vector, knowing the vector means knowing coordinates. So using these two radius vectors, we write down this formula to define a new vector, vector r. This vector is called the center of mass. Of the system of particles. Sometimes people call it the center of gravity, which is correct only if you have a uniform gravitational field. But if you have no gravitational field somewhere in the outer space, no gravitational field, then there will be no reason to call it center of gravity. It's better to call it center of mass of the system of particles. Why center of mass is important? Because when particles move at some velocities, at arbitrary velocities, we recall what is a velocity. A velocity is the rate of change of coordinates. So a velocity is the rate of change of coordinates. And the rate of change of vector r will be delta r over t, and here it will be the rate of change of this vector will be expressed as delta r1 over delta t plus m2 delta r2 over delta t divided by the total mass of the system of particles, and that is m1 velocity 1 plus m2 velocity 2 over the total mass of the system of particles. So what we obtained here is exactly the velocity of the compound particle if two particles have collided and stuck together. And the same formula is here. So the meaning of this rate of change of this coordinate is just the velocity of the compound particle. But the two particles considered here have not stuck together. They are not together, they are separate. They are separate. But the velocity of their center of mass, which must be somewhere here, the velocity coincides with the velocity of the compound particle in case these two particles stick together. So the reason behind this vector, behind the center of mass coordinates, is very simple. It's somehow related to the velocity of the two particles as a system of particles. This is the velocity of two particles as a system. That is the velocity of their center of mass. Center of mass is a very important notion and we will talk about it a little bit. Suppose the point O of our frame of reference coincides with this center of mass. So the point O, we imagine that the point O is here, is located here, at the center of mass. Then, in this particular frame of reference, vector r has 0 length. It's 0, because we measure the vector r from the point where it ends. So in this particular frame of reference, this will be 0. And therefore, in this particular frame of reference, we will obtain that the denominator of this formula is 0. So in this particular frame of reference associated with the center of mass, we will obtain that m1 r1 plus m2 r2 is 0. And therefore, r2 can be expressed in terms of r1. It will be minus some coefficient equal to m1 over m2 times r1. So in this particular frame of reference, vector r2, this one, will be directed, will have opposite direction, opposite to vector r1. It means that these two vectors are directed along the same line, connecting the two particles. And therefore, the center of mass of two particles lies on the section of straight line connecting the two particles, somewhere in between the two particles. And the distance from the center of mass to the particle, to the second particle, and from the center of mass to the first particle, these two distances are related in a very simple way. This formula allows one to calculate the center of mass easily. If mass 1 equals mass 2, then these two vectors are equal in magnitude, and the center of mass will be located exactly at the center of the section connecting the two masses. The center of mass will be here. If mass 2 is much larger than mass 1, then this coefficient will be much less than unity, and then vector r2 will be small and smaller than vector r1. And in this particular case, the center of mass will be closer to the mass m2 if it's great, if it's large. The center of mass will be somewhere here and farther from the light particle and closer to the heavy particle. That is clear from this formula. All these considerations allow one to calculate the center of mass of different combinations of particles. If we have not two particles but more than two particles, like 3 or 4, then we just have to add similar terms related to other particles, and also here we must add masses of other particles if there are more than two particles. And so if we have some solid body, for example, we have a rectangular plate. How to calculate its center of mass? We have to divide the plate into small pieces, each piece having some small mass, and then we have to use this formula and calculate the vector showing at the center of mass. And the result is obvious, because when we have two identical particles, m1 and m2 equal to m1, then center of mass lies in between them on this section. And so if we have a rod, a uniform rod consisting of many particles, then the center of mass of this rod will be again at the center of the rod. And so if we have many rods stuck together, like forming such a rectangular figure, then the center of mass will be in the center of this figure at the intersection of its diagonals. If we have If we cut such a circle, then its center of mass will be in the center of the circle, etc., etc. It's easy to understand where the center of mass is for any object if we have this formula. It will be a good problem at the oral exam for any student to calculate the center of mass, for example, of such figure, a rectangle with a cut off part of it. So if this was the center of the rectangular plate, uniformly distributed mass, and we cut out such a portion of it, then calculate the center of mass of this figure. This is a good problem for oral exams. Also, if we have a circular plate and we cut out the hole in it so that the remaining body is this one, how to calculate the center of mass of such figure? These are very good problems for students which are often offered at the oral exam in this institute. Well, for example, how to solve this problem? How to find the center of mass of this circle, of this circular figure? If we know the radius, and if we know that this radius, small radius, is just half the radius of the large figure, of the large circle. How would you solve this problem? Suppose we know the total mass of the large circle before this hole was cut off. The total mass before was this one. And so the total mass of this cut off section will be what? If the radius of the circle is 2 times less than the radius of the large figure, then the area will be 4 times smaller, and the mass of this cut out portion will be 4 times smaller than the original mass. If the mass m was of the original figure was this one. So the mass of the original circular plate. And then we took and then we cut out this portion. So this portion will have the mass m over 4, right? Because the area of this portion is 4 times less than the area of the large plate. So we know the mass of the remaining portion. The remaining portion here, and its mass will be m2 equal to remaining 3/4 parts 3/4 parts of the original mass. And this is m1 of the smaller mass is m1 and larger mass is m2. So the original mass, the original figure, the original body had its center of mass here at the center. What do we do if we take away a part of this figure? It's equivalent to introducing here a negative mass. It looks like we put here a negative mass. Negative masses do not exist in nature. But mathematically, it's the same. To take off the part of this body is equivalent to putting here a negative mass, m1, so that the total mass of this whole is 0, consisting of the positive mass, which is here, and the negative, which we put here. So we know the mass of the original body, and we know its center of mass, which may be 0. So in order to calculate the coordinate of the center of mass of the new body, which is somewhere on the x-axis, somewhere here, in order to calculate this coordinate x, this distance of the new center of mass from the center of the circle, what do we have to do? We have to put it this way, that the center of mass, we have to put it this way, that the total mass of the remaining body, m2 times x, equals the center of mass, which is coordinate, which is r/2, of the cutout body, m1 r/2. So this distance s can easily be found as m1 over m2 r/2. What is m1? We know this is m/4. And what is m2? Yes, we know this is 3 divided by 4 m. And we have not to forget about r/2. So what we get here is r/6. So this distance from the center of the large circle to the new position of the center of mass is just 1/6 part of the radius. That is, manipulating with positive and negative masses, we can calculate a center of mass, position of center of mass of different figures, including this one. Here we also have to manipulate with the negative mass added here. Or we can use some other considerations. We can consider this figure as consisting of two rectangles. One rectangular figure has the center of mass in the center, in the intersection of its diagonals, and another rectangular figure has its center of mass here. And so the center of mass of this figure must belong to this section and must be located somewhere here. So calculating is not a complicated problem, but you must just understand what the center of mass is. So again, the center of mass as defined by vector r, And the rate of change of this center of mass, the velocity of the center of mass, is the velocity of two particles which collided and stuck together to form a compound particle. And such a collision, when the two particles stick together, such a collision is called an inelastic collision. This is an absolutely inelastic collision when two particles stick together when colliding. Inelastic. In contrast to elastic collisions, when particles don't stick together but just like billiard balls go from each other after the collision. Another important thing which we have to discuss is the condition of static condition of a rigid body. This is very simple because it's a consequence of the second Newton's law. If the net force acting on a body is known, then the body has an acceleration. And if the body is in static condition, what does it mean static? It doesn't move. It's at rest. Then acceleration is zero. Then the net force is zero. The net force acting on the body is zero. That is the condition for static situation, the condition for the body to be at rest in certain frame of reference. In another inertial frame of reference, which is moving with respect to the first frame of reference, this body at rest will have some velocity, some constant velocity, with respect to another moving frame of reference. So the net force should be equal to zero in order for the body to be at rest. That is a very simple consequence of the second Newton's law. And that equation allows one to solve many different problems related to statics. So you must only remember that this is not the single force, but the net force, the vector sum of all forces acting on the given body. For example, just let's consider a simple example. Let's consider a ball of a given mass, and the ball is tied by a thread here, and another thread is here. So two threads keep the ball in this condition. And there is certainly some tension in the first thread and some tension T sub 2 in the second thread. And certainly we consider this situation on the surface of the planet Earth, and here we have gravitational pull directed downward to the center of the Earth. The ball is at rest. It's in static condition. It doesn't move, and its acceleration is zero. Its velocity is zero with respect to you and with respect to this blackboard, but if you go to another inertial frame of reference which is moving, then the velocity of this ball will be constant vector. But again, the velocity may be constant with respect to some reference frame, inertial reference frame, but the acceleration will be zero because the velocity is constant. So acceleration is zero means that the body is at rest. And we have to find the condition of this situation. We have to find forces of tension here and here. How do we do it? We have to use this equation, the condition for static equilibrium of a given body. The net force equals zero. What is the net force? The net force is the vector sum of all forces acting on the body. And the vector sum must be 0. That is, the net force is 0. The net force is the vector sum of all forces acting on the body. Each term in this equation has its own magnitude and direction. We know the direction of G. It's indicated here. And we know the directions of these forces. We just don't know the magnitude. And we have to find the magnitudes of these two forces. Let's imagine that these two, let's assume that this thread is directed at 45 degrees to the horizon. We can choose any other angle. We can choose, well, the situation may be different. It may be 60 degrees or 25 degrees, any angle. But we have to specify some concrete angle in order to solve the problem. We can certainly solve it in general case when the angle is just alpha without specifying its concrete value. Okay. In order to solve the vector equation, we have to consider this equation in two projections on two axes. So we have to choose convenient axis. A convenient axis is one vertical and another horizontal. So this will be x-axis and this will be y-axis. Horizontal and vertical axes. And we can now consider projection of each vector on the axis. So first, consider projection on axis x. T1. Vector T1 is directed in the negative direction of x-axis. So its magnitude will be minus T1 without any vector sign. This is the magnitude along the x-axis. Vector T2 will have its own projection, which can be calculated as T sub 2 with the plus sign because it looks in the positive direction of x-axis, cosine alpha. And vector G will have 0 projection on x-axis. So 0. And now consider the same vector equation as it looks from the y-axis. A projection of vector T1 is 0 on the y-axis. A projection of mg is negative because the y-axis is directed upward, so minus mg. And projection of vector t is positive because it will look in positive direction. It will be t2 sine alpha. And that must be equal to 0 because of the static condition of our body, condition of static equilibrium. So the vector equation can be reduced to two scalar equations. Equivalent. Two scalar equations are equivalent to one vector equation. Certainly, if we choose different axes, then the scalar equations will be different. They will have different terms here. We could have chosen some other axes. For example, we could have chosen axes like this, x and y. In this case, the coordinates of each vector would be different and the scalar equations would be different. But the final solution will be the same. The final solution for the magnitudes of these forces of tension will be the same. So you choose any coordinate system to solve the problem. And among many possible coordinate systems, you choose the one which is most convenient for the given problem. There is always some convenient system reference frame. Why is it convenient? Because in both scalar equations, one term is 0 if we choose the axis in this way. Well, that's convenient. Okay. Now, from the second equation, we can immediately obtain the value T2. It will be mg over sine alpha. And if alpha is 45 degrees, then the sine of 45 degrees is square root of 2 over 2. So the magnitude of this force will be easily calculated, and this is certainly 1 over square root. So can be easily calculated as mg square root of 2. So that will be the magnitude of the force of tension F2. If we know T2, this coefficient is known, and then it will be very easy to calculate T1 from this equation. The magnitude of T1 will be what? Just T2 cosine alpha. And T2 is known. This expression should be substituted for T2 here. So we obtain mg cosine alpha over sine alpha, which is mg tangent alpha. But if alpha is 45 degrees, then tangent of 45 degrees is just unity. So we obtain the magnitude as mg in our situation when alpha is given and is equal to 45 degrees. So we have found both forces of tension in both threads indicated here. Such is the way to solve problems in statics. Any questions? I have shown you the usual way of solving problems when we have the initial vector equation and we write it down in detail, taking into account all the forces acting on the body, and then we find projection of this vector equation on the axis of some reference frame which we have chosen. That is the usual and most general way to solve problems in statics. Certainly, there is other possible way of considering this problem. For example, we can find graphically the two forces, the sum of two vectors. In order to find the sum of two vectors, we have to form a parallelogram on these vectors, and the sum will be equal to the diagonal. That will be the sum of two vectors, T1 plus mg. Vector r, for example, equal to the sum of two vectors. And as the ball is in static equilibrium, then necessarily vector r is equal in magnitude to vector t and oppositely directed, because the total sum of r plus t2 must be equal 0. So from this, from consideration of this triangle, And if this angle is 45 degrees, then we find that this is an isosceles right triangle, and one leg is mg, another leg in magnitude must also be mg. So T1 must be equal to mg, just geometrically the same, which we have obtained using algebraic methods. Geometrical method gives you the same, because this angle is 45 degrees. So this leg must be equal to this leg. And if one leg is mg, then another leg is also mg, and this is just the tension T1. And so tension T2 must be something like the same. T2 must be equal to r. And vector r is larger than the leg T1. Larger because this is a leg, and this is square. R must be equal not as a vector form, but as a in magnitude. The length of this section must be mg square root of 2, if this is 45 degrees. So geometrically we have found this vector, and it must be equal to this one. So this is T2. And the answer must be the same, yes, the same as before. So it's possible to solve such problems analytically or geometrically using the figure indicating, showing all the vectors and geometrical relationships, or using the algebraic equations. Both ways are possible. Any questions? Just a few final remarks before the end. When do we have the end of this lecture? At what time is the end? 35 minutes or what? 1:35. Okay. I would like to make a final remark. One young man told me recently, one young person, a student, told me, well, all these masks are useless, absolutely useless. Why do you want to wear the mask, to put it on? It's useless. Because the virus particle is so small that it can easily penetrate through this material. Such was the reason behind the conclusion of this young man. So if we draw this material, we will, if we look at this material through the microscope, we will obtain that it contains of such structure with some holes in between the threads. And the virus particle is so small that it can easily penetrate through this material. No use in masks. Such was the opinion of that young man. Do you agree with that? Why not? The virus particle is very small, actually.
It needs something to go out of your body, like saliva, and saliva is bigger than pores and masks.
I agree, but not with chirurgic masks, because these are special for virus, but like when it's just for like, ¿cómo se dice? Like a normal mask, not
Well, I tell you what, it's true that the virus particle is so small that it can easily penetrate through this material. That's true. But another truth is as follows. Virus particle practically never travel alone. They always travel inside a droplet of liquid. A droplet of liquid containing hundreds of virus particles. And the droplet of liquid is always originating when you breathe. When you exhale air, when a person is breathing, it's easily observed that when we breathe, there are a lot of small particles of water. You have to blow on a window, on a glass, and you will see just a small, just a very thin layer, just like a misty reflection of light. So you will see that when we breathe, each person produces thousands of small droplets of water, very small, less than a micron or about a micron. And each droplet of water may contain hundreds of virus particles if the person is contaminated. And individual virus particle can easily penetrate through the mask, that's true, but this droplet of water cannot. It will be stopped by the mask. That's the reason why we should use masks always if there are people around us. It stops the small droplets of water. That's it. And virus particles propagate inside these small droplets of water. That's why the mask is useful, absolutely necessary. It stops the virus particles. There was such an experiment. In one cage, there were mice, and in another cage, that was a wall, and in an adjacent room, another cage with mice, and here was a window closed by such a mask. The mask was put on the window, on a hole between the two cages. And the mice here were contaminated, and the mice here were not contaminated. They were healthy. And the mask which was put here stopped viruses, and the mask stopped propagation of viruses. And actually, the virus contamination from this cage did not penetrate into this cage. And for many days, the mice living here remained healthy because of the mask here, which closed the hole between the two cages in this way. So experimentally, it's proven that the mask is very useful, regardless of the fact that an individual virus particle can easily penetrate it. Regardless of this true fact, the mask is very useful, because virus particles practically never fly separately, alone. They fly inside small droplets of water. That's what I wanted to tell you at the end of this lecture. So don't forget about masks, and don't forget about social distance, and let it be the end of this lecture.